Thank you. Always fun challenge for people to try and pronounce my last name. Um, as you can hear, I'm probably, maybe you can hear, I'm a little bit under the weather today. Let's not make that a problem though. Landed in France about 2 days ago. Moment I landed, happened to feel a bit catching like some kind of bug. And also, my flight was late by 17 hours thanks to BA. But it's always fun to be in this kind of rooms in robotics because we always have a really diverse crowd of people from the backgrounds we have sort of software people, AI people, usually hardware people as well, in the context of robotics, rhythmic, and electrical engineering problems and so on. For myself, I got into robotics when I saw, and this was probably a big moment for all of you as well, when I saw ChatGPT and the incredible innovations you can have within an AI that can work inside a laptop. But if you can take that out of the laptop and put it inside a robot body, you can have sort of 10 to even 100 times more impact. And this is the kind of rooms where those developments are happening, so I think we're all in the right place today. And here's a particularly impressive piece of research from Stanford University. It's called Mobile Aloha, and the researchers there managed to teach a robot to cook shrimp. It wasn't number one on my list of tasks to be automated, but here we are now. And this sort of made me, this came out last year, beginning of last year, and made me go all in into robotics. Let me actually put a timer so I don't go over. Made me go all in on robotics. So I went in and bought a robot. This robot is in my flat in East London. It's a relatively small flat, smaller than this room. So the robot takes up a non-trivial portion of the floor space. It's also a fun story. It came in this like giant truck that's clearly not designed for like apartment buildings. The robot was in pieces in these two large wooden pallets, and it was actually fun because the heavier of the two pallets had like about 2 centimeters of clearance from the lift doors. It would have been fun to figure out how to get it up there, because I live on the 11th floor, if you don't fit in. And I thought sort of I'm gonna start doing some open source work on the robot, collect some data, train some models. We're gonna have this whole AI problem for robotics solved in a few months. It turns out it wasn't quite that simple. Ended up being, much harder than I thought. But over the past, 6 months to a year that I've been working in robot AI in open source, I've learned quite a bit of things, and this presentation is basically my opportunity to share some of those things with you. And the particularly most interesting thing I want to talk about are VLA models. If you don't know what VLA models are, they are sort of the attempt to build a robotics foundation model. They are an extension of vision language models to the action space. So basically the robotics community's answer to models like ChatGPT and Claude. So the idea here in action space is that we can instruct the robot. Do I need the microphone? Do I need a microphone?
That's fine.
Okay, let's do without. So the robot world's answer to basically ChatGPT. So we can encode robot actions as well as their proprioceptive state. Actually, us humans, we are told that we have 5 senses, but we actually have way more. So for example, I don't need to view my arm in order to be able to tell where it is. Similarly, robots, we want to encode the position of the arms themselves. We humans also have things like balance in our inner ear that maybe humanoid robots could need as well in order to balance, because it's known as a challenge. In addition, I would talk about the open source side of this rather than necessarily cutting edge stuff, what's happening inside labs, because that's something that all of us have access to, whereas there's stuff happening in cutting edge labs only available for some people. And I also want to talk less about the research and more about the practical applications. Basically, what does it take to build actual real applications on VLA models today and in the next 12 to 24 months. And the sort of theory on why we're doing this in the first place really relates to what we've seen in other fields. Natural language used to be sort of humans encoding our own assumptions into how language works. English language grammar looks kind of like this, French language grammar is like this. So then if we look up some rules in the English language and we translate it to the French, we might be able to get some good things out of it. But as it turns out, humans speak like textbooks, we do not. So it ended up being that actually just looking at trying to predict the next token using this giant transformer model was the way you ended up solving language rather than trying to build a massive sort of model based on our human assumptions of how we speak. And vision went through kind of the same trajectory as well. I always loved this particular comic from 2014, where you said that in order to be able to tell birds from not a birds, you had to use sort of 5 years of research team as time, which ended up being remarkably correct in the sense that today it's basically a trivial task. You just call the ChatGPT API or something. And this same dynamic is happening in robotics as well. Here's an example from Physical Intelligence, which is a startup in San Francisco founded by the same researchers who made the shrimp cooking robot Mobile Aloha earlier. And folding t-shirts like this is incredibly complex. It doesn't feel complex to us humans because we do that every time we have to do laundry. But for robots, it's just very unpredictable to handle cloth because it folds, it kind of moves around when you grasp it, whereas so-called rigid body objects like this microphone are much easier to deal with. And just by collecting data and by training a poly-sci without any assumptions of how the robot should be able to do the task, they were able to complete it in very robust way without needing to program sort of motion plans or grasp positions, which is what people used to do in the past in robotics. But Physical Intelligence, they have sort of hundreds of millions of dollars in research funding, VC funding. You might think, okay, well, they can do this stuff, but how can I, as a member of the open source community, start building applications like that? Where do we even get started? First, we need a robot. This isn't talk about hardware, but it is worth mentioning that basically the state of hardware available to researchers today is just so much greater than it was like 3 years ago, even greater than when I got started last year. We didn't have low-cost robots like the SL100, which is this cheapish arm here, assembled from 3D printed parts and cheap servo motors. This setup here costs about $300, or more like, I guess, 300 euros, more in dollars now because of what's happening on there that we're not going to get into. And it consists of a teacher arm, which is this one that looks like a little gaming controller, and then a real follower arm, where you can basically mirror any actions from the teacher arm into the follower arm. And if you want to go a little bit higher end on the price, you could go with Poland Robotics' Ricci, which is a French humanoid robot. I think we have some Ricci Poland people here in the room as well. I think Ricci costs sort of in the price of a luxury car, so we have quite a big range of different robots to choose from. But it's interesting that all the AI models and the techniques that we're using work pretty much equally well on these kind of low-cost, cheap research arms as they do on like proper high-end research humanoids. Of course, the capabilities of the hardware are going to be different, but from the AI's perspective, it can sort of handle all kinds of bodies. And a big change in AI robotics that's happening compared to more traditional robotics is that it tends to be quite Python-driven. That's because as AI researchers, we deal with Python code, we train our models in Python. Our data sets and data operations usually happening in Python as well. If we can also control the robots from Python directly, rather than having to rely on various kinds of other frameworks, it would be nicer. And that's what Hugging Face's Le Robot library is trying to address. This is not a talk about Le Robot. I'm not sure if there is one about Le Robot specifically in this conference. If there isn't, then I recommend everyone to take a look at it. It's probably the sort of leading AI robotics library that's open source today. And I've been privileged to be able to work with some people in Hugging Face over the past 6 months. It really is a great project. And in terms of the VLAs, so if you have one of these vision language action models, how do you actually start using it? The problem is that today's VLAs don't work zero-shot. So what that means is that if we download a vision language model checkpoint, let's say a Mistral model, we can just start using it. Like we can just start calling it, we don't need to do any kind of fancy training operations or something. That doesn't work in the VLA world, in the robotics world, because our hardware is different, our environments are different, and our tasks are also different. So we don't have the level of generalization required for what we call zero-shot operations, certainly not in open source today. And that's why we need to fine-tune these models with our own data. And when we talk about robot data, people sometimes think, okay, what does that really mean? I know Minlan just gave a great presentation of their fine-tuned robotics project, which could answer some of those questions, hopefully. But here's a practical thing on like what we mean by robot data. I have a setup where the back arms of my robot are basically modified controllers that I can use to mirror to the front arms, and I can use this to just do the same task over and over again, record the video, record the state of the robot arms, and then we're going to be using this dataset to fine-tune a pre-trained model to be able to do the task for us. And in terms of VLAs, what we could use to choose from, there's quite a large list of them that are available today. Probably the best one to get started and the easiest one to get started with is Pi0 from Physical Intelligence. That's the model that we just saw folding laundry earlier. It's available in Hugging Face's robot library, so you can sort of start using it as it is. Not zero-shot though, you still need to fine-tune it, but it's probably a good one to get started with. It does have a problem in the sense that Pi0 was designed for this kind of research arms, 6 degree of freedom robot arms. If you have, let's say, a humanoid robot, Pi0 might not work as well on that. So NVIDIA trained their model, Groot, specifically with humanoid robots in mind. It does control many kinds of robots, but they sort of said that humanoids are their main intention. So if you're using a humanoid form factor, you might want to get started with something like Groot. RDT here is a very interesting project. Minlan's presentation included them in one of the corners. It's one of the earlier open source models that came out, one that I've been able to work a little bit with as well from Tsinghua University. What they do differently is they allow multiple different ways to format the robot state and the actions. So when we talk about like robot actions, we can actually encode them as joint positions, so joint angles. We could encode them as velocities, torques, the end effector position in like X, Y, Z space, or the relative or absolute position. So there's actually many different complexities in there. And if you have many data sources and you have to sort of merge them together, it can kind of be a problem in many of these ways. RDT has like a very neat sort of way to encode these all natively inside the model. So you can handle many different data sources together. And if we just spent the presentation talking about existing VLAs today, we would go out of date very, very quickly. Probably in like 3 months, this presentation would be useless because there are so many research papers coming out on this space. Probably more came out since these slides were made, in fact. So I actually think we should talk less about the models themselves and more about the real problem that we have. And the real problem is data. Robotics is a data problem. The thing about vision and language is that we have large existing pre-trained datasets to choose from. We have the whole internet. We have all the books in the world, all of Wikipedia, all the TV and videos. There are copyright reasons, yes, copyright issues, but we have large amounts of data. With robotics, we just don't have that data. So robotics data is actually highly valuable. And every company that wants to build something in the robotics space, even if you're building generalist AI, but especially if you're building hardware and you want to train an AI model to control your particular kind of hardware, everyone needs to collect their own data, needs to build their own data assets, as they're called. And while the models may go out of date in like 6 to 12 months because people are going to be training better architectures, the datasets should not go out of date in 6 months. You don't want to be collecting the same large dataset every 6 months. You don't want to be investing hundreds of thousands, if not millions of dollars, only to see that dataset go unused because researchers don't want it anymore. So we should be focusing a lot on the quality of our data. Here are 2 examples. On the left here, we've got the mobile Aloha dataset for washing a pan. This is from the same project that cooked the shrimp. So once the shrimp has been cooked, the robot sort of begins here, it turns around, it washes the pan under the sink and then puts it on the dryer. It's a relatively complex task with mobility and moving the arms and all that, but the operator was able to collect this whole trajectory in 22 seconds. the data is collected in like relatively high resolution and at 50 frames per second, which is, that's a lot of frames. While on the other hand, there's an older dataset here from sort of cooking, so we're moving a pan into the stovetop and lifting the pan's handle or the lid. And in the older dataset, when the sort of engineering around the control system wasn't as mature, it took the operator 3 minutes, almost 3 minutes to collect this. The images are sort of much lower in the resolution. It's 128 pixels here, and we're only recording at 5 frames per second. So if I was training models today, I would find it much easier to use datasets like this one, better quality datasets than some of these older ones. And if you are designing like a data collection system for your robot today, you want to make sure that any of the data you've invested all that money into collecting today is still going to be useful 5 years from now. And that's true not just for companies, but also for open source people. You want to be working on iterating on your models, not on collecting more data manually in your room or wherever you are. There's actually been remarkably little research going into the actual qualities of good datasets. I wish there was more. So this list here is kind of vibes-based. It's based on my experience and what I see as being valuable. So you want the images to be relatively high resolution. Even though many of the vision models, vision encoders we use today, actually tend to compress the images further, we want the datasets to have relatively high resolution just for future's sake, because in the future we might have vision models that don't need to do this kind of compression. We want a high enough frequency on the frames per second, but more importantly, we want the frames to be consistent, because when we're pushing in large amounts of data through our systems, like USBs and whatever, camera images and so on, we might sometimes see lag, or we might see frozen frames, for example. That's not going to be good for your model's learning if you have this. So it's probably better to actually have clean, lower FPS datasets than sort of high FPS, but very laggy frozen frames on the cameras sometimes. You want to move your robot fast. That's because today's models are trained using what we call imitation learning. So I, as a human, do the task as a robot, and then our AI model just learns to mimic those movements. It has no way to optimize that movement, unlike something like reinforcement learning, where you can tell it faster equals better. With imitation learning, we can't do that. So if we control the robot slowly, our AI is going to move slowly. It's kind of simple as that. So we would like to move the robot fast, but more importantly, we want to move the robot in a stable way. If we start shaking, either because my hand shakes or because of the system that we have sort of fluctuates between two different positions, then our AI model is going to learn that shaking at the same time. In fact, it might even make it worse. So shaking, no good. We want target objects to be visible in the frames. That sounds really obvious. Why would they not be visible? But usually when we're collecting data, I'm looking at the scene from somewhere high up in here, and my camera is looking at it from somewhere like here. So it's quite easy actually to accidentally leave out part of the scene when you're collecting your data. And while you want target objects to be visible, you don't want yourself as the human to be visible. If you have one of your arms visible in there moving together with the robot, your AI model is going to learn to track the hand and the arm and not the objects. So you're going to notice that it doesn't work and you have no idea why. If you have access to wrist cameras, so a camera in here, that's going to be very helpful for your learning. The main reason for that is that we don't have any tactile sensing in robotics today. So if I touch something, I don't get any feedback from the touch. But if I have a camera in here, I actually do get feedback from that. It's also much easier to do grasps if you have much clearer look. And you want the sight to be not dark. That's because sort of human eyes, very good at handling darkness. Cameras, maybe not so. Data diversity is another big topic. Basically, we always talk about the size of our datasets. We want large datasets. If size of dataset was all that mattered, we could go into a factory, hook up a computer to one of the industrial robots doing the same weld like 100 times a day or 1,000 times a day, and say that's 100 gigabytes of dataset right there. But just collecting the same trajectory in the same environment over and over again, there's no point in doing that. We're not going to learn anything useful out of that. we want to have a large, diverse data set. And the most obvious way to do that is to just collect data in many different places. Physical intelligence allegedly is renting Airbnbs to take their robots into many different, kitchens, many different bedrooms, many different living rooms. But moving robots is very challenging. You need to put them in vans. Maybe you need pallets, like I said earlier. Not fun. But if you use creativity, you can actually create quite diverse scenes, even in one room. These are all from my flat in the same room. And we varied the objects in the object position. We varied the objects in the background. I have access to sort of colored lighting, so I can change the lighting using my phone to be like warmer, darker, red hue, blue hue. That's actually a very underused technique. I wish more people knew about the lights. We can add a tablecloth or like a t-shirt or something on the table to make the background look different. So you could call this data augmentation, but actually augmenting the real world rather than post-processing the data. And it has been quite useful for me at least. We can also change the viewpoint of the camera so we can face to the other direction or so on. And I said there hasn't been too much work on grading our datasets by their quality, but here are some of the recent work that I did find. Value order correlation. Here is a proposed metric that relies on the fact that imitation learning today considers robotic manipulation as what we call a Markovian process. Markovian. That's a complex word, but it basically just means that my next action only predicates on where I am now and not in the history of all the past actions. So if I'm in here, I only consider where I am right now and not how I got here. So the idea behind this is that at every point, if we want it to be super clear what the robot needs to do next. So we don't want our data to contain like movement back and forth, because our AI model is going to get confused, it doesn't know what to do next. And their idea was to basically shuffle all the frames in the dataset and then give it to a VLM and then ask that VLM to unshuffle them, put them back in the original order. And the theory is that if the VLM does a good job, this dataset is very easy for AI models to learn via imitation learning. If it really doesn't know what to do, then it's considered to be a lower quality dataset. Demo score is basically a way to curate an existing dataset with many episodes, where the episodes themselves might be of varying quality. The idea there is that if we can detect which episodes within the dataset are less good, we might be able to remove those automatically, and then only focus on a smaller but more focused dataset, which might give us better results. So the idea is that actually by deleting some data, we might get better results than just training on everything. And I wish there was actually more work happening in this space, so if there's any researchers in the room, very, very good place to start. Yeah, most of this talk, I acknowledge, was spent on talking about data rather than on the AI models themselves. That's a bit of a bait and switch, but it really is because robotics is a data problem. And the models themselves are going to be changing. Models themselves are sort of developed by people in these fancy labs. Maybe some of the labs are here actually. It's something that us in the open source certainly don't really have that much ability to change. But what we can do is we can work on the data side. We can work on building high quality data assets and so on. So that when good models do come across good open source models, we can then take our own existing dataset, fine-tune them on that, and then get good results. And I think it's actually such an important problem that I've started to sort of tackle it myself. These screenshots that you saw during the talk were all from my recently built application called PicoData. The idea here is to build a UI, an application for cleaning your datasets, curating your datasets, and sort of trying to solve the questions of like what makes a good dataset in the first place, both manually but also automatically. We're still in private beta, but if you guys are working with robot datasets and want to know sort of what makes a good dataset, is my dataset good, and how to fix those things, then I do recommend taking a look. Okay, actually a bit early on my talk. but we're finally getting into the training and the inference side. The reason why I spent less time talking about this is because we know how to train AI models. And actually training robot models is really not that different from any other kinds of AI models. We have datasets, we have compute, and we use them to train them. The main differences, I would say, is that firstly, these VLA models, they're quite large models, and we tend to train them on the cloud rather than on sort of commercial grade GPUs that you might be using to train locally. There are people who are trying to solve this problem via low-RA fine-tuning or other parameter-efficient fine-tuning methods. Let's hope for more work in there. It will be good for open source people. And then secondly, in other AI contexts, people always have sort of training and test data splits. In robotics, we actually don't tend to use test sets. And people say, why are you not using test sets? That's crazy. That's because we test our models in the real world. So we don't really care whether a model did, X% on some withheld test set. What we really care about is that if we take the robot, we put it in front of a table, and we put the objects there, we ask it to do something, what's the success rate in the real world? So that's why we don't really care too much about having a training and test set separation, because we evaluate our robots actually in the real world. And this does make robot models harder to evaluate, because you have to have sort of standard systems or standard setups. If lighting changes, if the position of the robot changes, you might see differences actually between different days, and so on. And getting into the inference side, once we've trained one of these VLA models, how do we actually run them in the real world? And if we have a complex enough task, let's say fold a t-shirt, people have noticed that just prompting the model with fold a t-shirt is usually not enough. That's because there are so many steps to just folding a t-shirt. So what people have realized is that if we can decompose that prompt fold a t-shirt into subtasks, like, there's no t-shirts in here, but there's like move your left arm towards the microphone, grasp the microphone, and so move your arm up, move your arm down, release the microphone, move your arm back. So very, very simple subtasks. You can actually get quite high performance. And if you do this sort of chain of thought or subtask annotation in your training datasets as well, you notice that all these very different problems, like anything from opening doors to picking up objects to folding t-shirts, they all kind of seem quite similar. It's just moving arms towards certain positions, picking up objects, and so on. So this idea of training on subtasks, which I think is similar to what sort of Minlan's project earlier involved, has become popular. And if you take that same idea to its sort of logical conclusion, you get to the helix architecture, which is what Figure AI proposed, where you have sort of two systems. One system is higher level, running on the cloud, with large access to very large amount of compute resources. That's giving you sort of the high level understanding of what to do. And then one system that's running on the robot itself have access to much lower power levels, much lower compute possibilities, but is able to give you sort of fast closed loop control. One big difference with these AI models that we use today is that they're able to recover from issues, which I think we have in the second slide. So this is a Easter themed demo that I recorded with Pi0, fine-tuned Pi0. It's not perfect, as you can see, so don't judge me on this. But here you can see some pretty interesting examples of error recovery, where because the model is just constantly predicting what it should do next, if it fails to grasp one of those objects, as it often does, because it's quite complex to grasp them, it just automatically replants. There's no need to decide, we're going to replan, we're going to do it again. And one thing that you notice at the same time is the robot sort of moves, it stops a bit, it moves, it stops a bit. That's all happening because we have latency issues. So we're running this large VLA model in a 49-bit GPU. There's, half a second of latency every time we predict a new chunk of actions. And it's not perfect, as you can see. The robot in here sort of failed to put the Maltesers back in the basket. And because that example isn't in the training set, so it's not able to recover from this position. Which actually gets us to the next stage, which is that there was actually a recent demo from one of the startups that showed how to get to 99.4% accuracy for a single task in a highly constrained environment, which I find very impressive. But when we talk about many tasks and diverse environments with a lot of sort of disruptions and changes, we are probably going to struggle to get to 100% accuracy or even to 99% accuracy anytime soon. And the problem with us trying to use these robots in the real world is that we don't really want like 80% accuracy. If you were doing dishes, you ask the robot to empty your dishwasher and sort of 4 out of 5 plates it correctly put inside your cabinet, and the 1 out of 5 it drops and you have a mess on the floor. I don't think any one of you would hire that robot. But if we can't get to 100% accuracy within the robot model, the foundation model itself, could we run some other model on top of it to try and predict when it's about to do something wrong, and then sort of use a human to teleoperate the robot at those times? So if the robot itself isn't able to get to 100%, can robot plus human do that? And it's interesting to me because this is actually the approach that was taken in self-driving cars, and that's what sort of maybe Professor Yang was able to tell a little bit more on the self-driving car side. Because the autonomous driving people, they didn't ship a robot taxi that drives by itself from day one. They started from autopilots, like a Tesla autopilot that's able to drive for you, but if the autopilot doesn't know what to do, it hands control back to a human. And maybe that's something that we have to do in the robotics side as well. And I'm sort of highlighting a paper in here from Indian Robotics Lab. I think this is in, it's somewhere in America, Carnegie Mellon University, I think, where they were able to sort of train this robot model that would stop the robot from causing the Maltesers to fall from the back. And this is kind of work that really excites me because it gives us the opportunity to sort of bridge the imperfect model with human aid to get sort of 100% reliability. And the sort of highlight of all of this, I would say, is that all the major components of the VLA stack are open source. So we don't need to reinvent the wheel. We don't need to start designing our own architectures and have hundreds of millions of dollars in compute budgets to be able to start building with this technology stuff. We can just use the existing open source blocks, and our job is to combine them into something useful. And people for a long time actually have said that robotics is an integration problem. So we need to integrate the hardware, the sort of low-level controls, the AI models, the data, the training and compute, and all of these, all the sensors as well, into one cohesive application. And here's some good examples from the last The Robot hackathon that happened here in Paris about a month ago. I think, yeah, it was The Robot, so from Hugging Face, Mistral AI, Entrepreneur First, who was sponsoring this. Alb Maria here was in a team where they developed a robot to pick out rubbish from a pile of sand. I think they used simpler, smaller AI models rather than a foundation model that was fine-tuned for the task. But in a couple of days, they were able to build something that was about to do, able to do the task, able to pick out rubbish from this pile, which I think is a pretty impressive example of how even in relatively small time frames today, thanks to open source, we can all build an AI robot that can sort of do some task, some amount of time. The problem is, of course, getting from some amount of time to all the time, and we don't still have necessarily great stories on how to achieve that. But the real sort of thing that I would say is the real deployments in the real world and not inside labs are what's needed to produce real data. And we need real data to sort of get the data flywheel going. So yeah, let's kickstart the data flywheel and try to bring these robots to the real world. Thank you.